We're in section 3.4, optimization and elasticity of demand. A function may have more than one relative maximum or minimum. It may be important in some cases to determine which value is either the largest of the large or the smallest of the small. Remember, relative extrema were discussed back in section 3.1. Now we're going to discuss absolute maximums and minimums, and also relative extrema. Another word that we used for that was also local extrema. So an absolute maximum is the largest possible value of a function, and it can be an endpoint. And then an absolute minimum, the smallest possible value of a function, also can be an endpoint. There's a graph to the right, and you can see the highest of the high point is going to be our actual, not just our relative maximum, but would also be our absolute maximum. In this case, because we have the endpoints pointing up, there is none that's going to be the highest of the high, so we would have no absolute maximum. But in terms of an absolute minimum, we do have an absolute minimum. This value down here at point R is going to be the smallest of the small. If you notice, as the smallest y value, or the most negative y value that we would have. Extreme value, or extrema, of f of x are the absolute maximum and minimum values of the function. Singular would be extremum. Let f of x be a function defined on domain D. We say f of c is the absolute minimum of f of x if f of c is less than or equal to f of x for all x in our domain. So the absolute minimum is the smallest y value over the entire domain, and we cannot use negative infinity. So that's why those endpoints are good to look at. Also, an absolute maximum of f of x if f of c is greater than or equal to f of x for all x values in the domain. The absolute maximum is the largest y value over the entire domain. And again, we cannot use infinity, and we saw that up above in the diagram. The next thing that we have is the extreme value theorem. If f is continuous on a closed interval a comma b, then f obtains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d on that closed interval a, b. So a couple things to note here is that we do have to have a continuous function. We talked about continuity earlier. And then this also needs to be over a closed interval, not an open interval. And looking at the two graphs that are given to you guys, the two examples, you can see where that global or absolute maximums and minimums are. The closed interval method, to find the absolute maximum and minimum values of a continuous function on a closed interval. So again, it needs to be a continuous function and on a closed interval, a comma b. First thing we need to do is find the values of f at the critical numbers of f on that closed interval a comma b. Make sure critical numbers are in the interval. If they are not in the interval, you can discard those. Step 2 says to find the values of f at the endpoints of the interval. Step 3 says the largest value from steps 1 and 2 is the absolute maximum value, and the smallest of these values is the absolute minimum of the value. So again, you need to find your critical numbers, make sure that they're in that interval, and then you also need to find the endpoints, and you need to substitute these into your function f. Then the smallest of the small is going to be your absolute minimum, and the largest of the large will be the absolute maximum. The next example that we have says to find the location of any absolute extrema for the function below. So if you look at this, we have a right endpoint that is pointing up to infinity. And so since that is going up to infinity, we have no absolute max. However, we have a closed endpoint over here on the left side, so we can actually find an absolute min. And so our absolute min is going to be the smallest y value that we have. And the point that has the smallest, most negative y value that we would have on here would be at -1, -3. The next example that we have says find the absolute maximum and minimum of our function f of x equals 2x cubed minus 15x squared plus 24x plus 7 on the interval 0 to 6. So a couple things to know. First off, we do have a closed interval. I provided the graph for us to kind of look at, but most of the time problems don't give you the graph to look at, but I wanted you to visualize it also. So first thing we need to do is find our critical numbers. So our critical values are found by doing f prime of x and setting that equal to 0 and also figuring out where it is undefined. This is our function is continuous, it is a polynomial, and we are dealing with a closed interval. So this is continuous. So our derivative is going to be equal to 6x squared minus 30x plus 24. And we're going to take our derivative and set that equal to 0. From here we can factor out 6 from all of these terms, and we end up with x squared minus 5x plus 4. And then this will factor also, and we end up with x minus 4 and x minus 1. From here, setting those each equal to 0, we get x is equal to 4, and we get x is equal to 1. You now need to look and make sure that 4 is in the interval from 0 to 6, and it is, and also 1 is in that interval, and that also is. So these are our critical values, our critical numbers. In order to figure out your absolute maximums and minimums, we need to substitute these values that we have for our critical values back into our original function. So I need to find f of 4, and I also need to find f of 1. In addition, I also need to find at the endpoint. So I need to find f of 0 and also f of 6. Substituting these all back into our original function, which I will go ahead and highlight up here. So substitute those values in to our original function. When you do and you substitute in 4, you get negative 9. Substituting in 1, you should get positive 18. Substituting in 0, we get positive 7, and substituting in 6, we get 43. Make sure to check those so you understand how to use your calculator. The absolute max is the largest y value that we have, which occurs when y is equal to 43, so this would be our absolute max. And the absolute max here, so our absolute max is going to occur at 6, 43. Then to determine our absolute min, we need to find the smallest y value that we have, and that is at negative 9 would be our absolute min. And our absolute min is going to occur at 4, negative 9. So again, you can only use this method if you are dealing with a continuous function and it's over a closed interval. The next example that we have, we're going to go ahead and circle, and we will work on that one together in class. And then the next example that we have says find the absolute extrema of the function f of x equals x minus 1 over x squared plus 1 on the interval from 1 to 5. So a few things to note here. This function that we have is continuous everywhere because x squared, our domain, plus 1 is never equal to 0. So this is going to be a continuous function from 1 to 5 or over the whole domain. And for this, it also has a closed interval. And our wording of absolute extrema means you need to find your absolute max and your absolute min. So in order to do this, we need to find a derivative first. So taking the derivative of our function requires us to use the quotient rule, which is the denominator, times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And again, that was discussed in the previous chapter. And definitely go back and make sure you know the derivative rules very well. So simplifying this, we end up with x squared plus 1 minus 2x squared plus 2x divided by x squared plus 1 quantity squared From here, we can simplify this a little bit more, and we arrive at negative x squared plus 2x plus 1 divided by x squared plus 1 quantity squared. And then I'm going to go ahead and set our derivative equal to 0. And this is going to be to determine where our critical values are. This requires us to multiply both sides by x squared plus 1 quantity squared, which is going to be that our numerator, negative x squared plus 2x plus 1, is equal to 0. This does not factor nicely for us, and not all problems will. And since this does not factor nicely for us, we are going to have to use our quadratic formula, which is negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. From here, we can simplify this. We have x equals negative 2 plus or minus the square root of, and we have 4 plus 4, which is going to be 8, divided by negative 2. And then simplifying again, we get negative 2 plus or minus the square root of 8 simplifies to be 2 square root of 2 all over 2, which then simplifies again to being 1 plus or minus the square root of 2. This is approximately equal to, it's a difficult thing to substitute in. I'm going to go ahead and substitute in an approximation for that. So if I go ahead and do 1 plus the square root of 2, I get 2.41, about, again approximating. And if I substitute in the negative, I would have 1 minus the square root of 2, which works out to be negative 0.41. And from here, since I'm dealing with a closed interval, I'm going to take my critical values, which I have as 2.41 and negative 0.41. However, negative 0.41 is not in our interval between 0 and 5, so I'm going to go ahead and cross that one out. And so we need to substitute in 2.41 into my original function, and then also my endpoints, which is going to be at 1, and then also at 5. So substituting these into your original function, which I will go ahead and highlight. Substituting in 2.41, we arrive at 0.21. Substituting in 1, we get 0. And substituting in 5, we get 0.15. And so your absolute max is the largest y value that we have, which occurs when y is equal to 0.21, and our absolute min would occur at the smallest value that we have, which is 0. So another way to write our answers are going to be the absolute max occurs at, our value is going to be 2.41, comma 0.21, and our absolute min occurs at, and the min that we have is going to occur at 1, 0. On the next page, it says for an open interval, so the examples that we looked at previously were over a closed interval. Rather than evaluating the function at the endpoints, we evaluate the limit of the function to see where the endpoints are approaching. And this is back from chapter 1. So we're going to be looking at the limit as x approaches positive infinity of our function, and then also as x approaches negative infinity of our function. So the next example that we have says find the absolute extrema, which again is our absolute maximums and minimums, if they exist, as well as the values of x where they occur. So the function that we have is f of x equals 12 minus x minus 9 divided by x. It does tell us that x is greater than 0, so we know that it doesn't include 0, and we know it goes on to infinity. So I am not dealing with a closed interval like we had before. However, it is asking for absolute extrema like it did in the previous examples. First thing we need to do is find our critical value. So we need to take a derivative, so f prime of x. And so in order to do that, we have the derivative of 12 is 0, the derivative of negative x is negative 1. And then to take the derivative of the third term, you can think of this as being negative 9x to the negative first, which is going to become positive 9x to the negative second. Setting this equal to 0, we get 9 over, I'm going to rewrite this as 9 over x squared. It makes it a little bit easier for me to solve. I'm going to add 1 on both sides, multiply both sides by x squared, and then take the square root, put a plus or minus. So I get plus or minus 3. So I need to also remember that x is going to be greater than 0, so I do not need to look at the negative one. So I'm just going to say positive 3, so x is greater than 0 like we saw up above. So from here I need to find f of 3 just like we did before, substituting in this into my original function, which again I will highlight up here. So when you substitute that in, you get a value of 6. Then I also don't have endpoints to look at. What I need to explore is looking at the limit as x approaches positive infinity of my function. My function is 12 minus x minus 9 over x. And as this approaches infinity, we arrive at 12 minus infinity minus 9 over infinity, which is just going to be going off to 0 like we saw before. And so this goes off to negative infinity, meaning my endpoint is pointing downwards, down to negative infinity. And then I also need to figure out what about the limit as x is approaching negative infinity. However, I don't deal with negative infinity in this problem, so I'm not going to look at that for this, but I need to look at my other end. And the other end that we have in this problem is not negative infinity. We're actually dealing with 0. So I need to approach 0, and I'm not approaching it on both sides. I'm actually only approaching it on the positive side. We're not looking at anything smaller than 0. So go ahead and put a little plus up there. And now I have 12 minus x minus 9 over x is my function that we are dealing with. So to figure this one out, I'm going to go ahead and substitute this in, and I have 12 minus 0 minus 9 over 0 from the right is something extremely small. It's also positive, and so I have a negative sign out in front, but it is also going to be equaling negative infinity. So both of my endpoints are pointing down, which means that I am not having an absolute minimum. So we can say there is no absolute min. And we do have an absolute max. And the absolute max is going to occur at 3, 6. Up here it does say to determine the x values. So this was also at x is equal to 3. The y value is at 6. The next thing in our notes we have is called the second derivative test to find an absolute extrema. It says let c be the only critical number of f of x, and suppose the second derivative is continuous near c, and the first derivative is equal to 0 at c. So first bullet point says if the second derivative of c is greater than 0, and remember then greater than 0 meant that this was concave up. And it says if it is concave up, or the second derivative at c is greater than 0, then f of c is an absolute minimum on the interval. And you can see this down here, that we would have an absolute min. Likewise, the second bullet point says if the second derivative of c is less than 0, then f of c is an absolute maximum on the interval. So if you think about our second derivative being negative, it means that this is concave down, and there's going to be an absolute maximum on that interval. The next example, we're going to go ahead and circle, and we'll look at that one together. It continues on to the next page. So all of that we will look at together. The next thing says that if the revenue derived from the sale of Q units is R of Q, and the cost of producing those units is C of Q, then the profit is P of Q equals R of Q minus C of Q, since P prime of Q is equal to the derivative of R of Q minus C of Q. which is the same thing as taking the derivative of our revenue minus the derivative of our cost. It follows that the derivative of P of Q is equal to 0 when the derivative of R of Q is equal to the derivative of C of Q. If it is also true that the second derivative of Q is less than 0, or equivalent that the second derivative of R is equal to the second derivative of Q, then the profit will be maximized. So we have the marginal analysis criterion for maximum profit. Profit is maximized at a level of production, Q, where marginal revenue equals marginal cost, and the rate of change of marginal cost exceeds the rate of change of marginal revenue. That is where the first derivative of our revenue and our cost functions are equal, and the second derivative of our revenue is going to be smaller than the second derivative of our cost. We also have the marginal analysis criterion for minimal average cost. There is a typo in there, so go ahead and write that as AC of Q. This states that the average cost is minimized at the level of production where the average cost is equal to the marginal cost. So that is where AC, our average cost at Q, is equal to the derivative of cost, which is our marginal cost. The next thing that we have is the elasticity of demand. The change in price of a product or service will change the demand of that product or service. One way to measure the sensitivity of demand to change in price is by relative change, the ratio of percent change in demand to percent change in price. Let Q equal F of P, where Q is demand at price P. The elasticity of demand is equal to E is equal to negative P over Q times dQ dP, so the derivative of Q with respect to P. Demand is inelastic if E is less than 1. What this says is that we would have a small change in price, has little effect on the demand, so this is inelastic. And then we have demand is elastic if E is going to be greater than 1. Small change in price has a more effect on the demand. And the demand has a unit elasticity if E is equal to 1. Total revenue is maximized at the price where demand has unit elasticity, or E is equal to 1. And again, maximum revenue is going to be at P times Q. So the next example that we have says, suppose the demand for a certain beverage is Q equals 24,000 minus 3P squared, where P represents the retail price of a case of the beverage, dollars per case, and Q represents the average number of cases purchased year by a consumer. Calculate and interpret the elasticity of demand when P is equal to $50 per case. So it does ask us to calculate and interpret elasticity of demand when P is equal to $50 per case. So the first thing that I notice that we are given is the demand function. Q is equal to 24,000 minus 3P squared, and P is going to be your price. So in order to find out our elasticity of demand, we need to look at that function that we have. And I'm going to write down the formula for elasticity. It's negative P divided by Q times dQ dP. And dQ dP would be taking the derivative of Q, which we have been given, and I'll go ahead and highlight that. And the derivative of this is going to be negative 6P. And then from here we have E is equal to negative P divided by Q, which again is highlighted. It's 24,000 minus 3P squared times dQ dP, which is negative 6P. From here we can simplify this, and we arrive at 6P squared divided by 24,000 minus 3P squared. And we're going to evaluate this when P is equal to $50. So substituting in 50, we have 6 times 50 squared divided by 24,000 minus 3 times 50 squared. When you work this out, you arrive at E is equal to 0.909. And so the demand is inelastic. If you look up above, E less than 1 is that demand is inelastic. So demand is inelastic. And so what this means is a small change in price has little effect on demand. So small change in price has little effect on demand. The next example that we have says for the demand function, Q equals 48,000 minus 10p squared, find E. So again, in order to find E, we have a formula that I'm going to go ahead and copy down first, and E is equal to negative p divided by Q times dQ dP. So we have our Q function that was given to us that I will go ahead and highlight. And we need to take our derivative, and we have dQ dP, which is going to be equal to negative 20p. And then E from here is going to be equal to negative p divided by Q, and Q is 48,000 minus 10p squared times dQ dP is negative 20p, and this simplifies to 20p squared divided by 48,000 minus 10p squared. And for this function, it was just asking for this is our value of E. So our E function that we have, depending on the price, is going to be 20p squared divided by 48,000 minus 10p squared. Part B, same problem, it continues on to the next page. It says values of Q, if any, at which the total revenue is maximized. So in order to find out where our total revenue is maximized, those values of Q, we need to look at when E is equal to 1. So we have unit elasticity. So I'm going to take the function that we had up above, which was E, and that was 20p squared divided by 48,000 minus 10p squared, and set that equal to 1. From here, I'm going to multiply both sides by 48,000 minus 10p squared, and we have 20p squared equals 48,000 minus 10p squared. I'm going to combine my p squareds together, and I have 30p squared is equal to 48,000 divided by 30. We have p squared equals 1,600. Taking a square root, we get plus or minus 40. And since this is our price, this can't be negative. So I'll put down can't be negative. So that means that we would have our price would be equal to $40, and this is going to give us our max revenue. So this question though is asking for the value of Q. So in order to find our value of Q, we know that Q is equal to 48,000 minus 10 times P, which we'll substitute in as 40 squared. Working this out, we get Q is equal to 32,000. So revenue is maximized when we sell 32,000 units. So we'll put down units. And it also asks for what is the total revenue that is maximized. So R of Q is equal to P times Q. And so our revenue that we would have when we were maximizing it would be 40 times 32,000, which works out to being equal to 12,800,000. So we have $1,280,000 for our max revenue. The next section that we have is section 3.5, which is additional applied optimization. And this says, in optimization problems, the goal is to maximize or minimize something, like volume, area, profit, cost. For each problem, you will need two things. First one is going to be an equation for what you're trying to maximize or minimize, and also a constraint equation used to plug in the first equation, so there is only one variable. Then you will need to differentiate the equation, find the critical values, and answer the question. So the first example that we have says you have been asked to design a 1,000 centimeters cubed can shaped as a right circular cylinder. What dimensions will use the least material? So when it talks about a right circular cylinder, if you don't know things as you're going through the homework, make sure you look them up. On an exam, I will make sure that I tell you guys shapes and also give you guys formulas, but homework, feel free to look up whatever you don't know and you can't remember. So a right circular cylinder is just a Coke can, if you think of it that way. And so we have two dimensions that we talk about. First one is going to be radius, and the second one will be our height. So dimensions that we talk about are going to be radius and height. And we're trying to use the least amount of material to make this can. So if you're going into any kind of business that deals with manufacturing of certain containers, you would definitely need to be able to do this kind of stuff. And this is using surface area. So the surface area is pretty much like if you were to use to wrap this can, what material you would need with it. And you want to minimize that, the least amount of material. So we have, also we know that this is a 1,000 centimeters cubed can. And that means that our volume is equal to 1,000 centimeters cubed. That's a volume that we were given. So the volume of a can, again, if you do not know, you would look it up, and it's pi r squared h. On a test, I would give this to you. So we know that the volume is equal to 1,000, but we don't know our radius or our height. This is our constraint equation. We are also asked to maximize or minimize something, and this one we want the least amount of material, so we're actually going to want to minimize that. In our surface area, if you were to open up the can, you would have two circles. You'd have one on the top and one on the bottom, and then that center part would have rolled out and it would have been a rectangle. So the surface area that we have is equal to 2 pi r h plus 2 pi r squared. And we want to minimize this. So we want to minimize our surface area. And with only one variable that we need to have in this, right now we have two. We have radius and we have height. Pi is just a number, so that is not a variable, that's not changing, that's a constant. So what we're going to go ahead and do is I'm going to solve for one of the variables in my constraint. It's easiest to solve for h. So if I were to solve for h, I'd have 1,000 divided by pi r squared. And I'm going to take this and substitute it in to h in my surface area. So when I do that, I have a surface area of 2 pi r h, and h is 1,000 divided by pi r squared, plus 2 pi r squared. So simplifying this, first one pi would cancel, one of our r's would simplify out also, and we end up with 2,000, 2 times 1,000, and then r to the negative first. And then the second term we have 2 pi r squared To find out where anything is maximized or minimized, we have to go ahead and take a derivative. So I'm going to take the derivative of our surface area formula with respect to the radius, since that's our variable here. We have negative 2,000 r to the negative second plus 4 pi r. I'm going to set this equal to 0. When I do that, I'm going to go ahead and move the negative 2,000 over r squared to the other side, and we get 2,000 over r squared is equal to 4 pi r. And then I'd multiply both sides by r squared and divide. We'll do that first. So we have 2,000 equals 4 pi r cubed. From here, I'm going to divide both sides by 4 pi to isolate my r cubed. So we have r cubed is equal to 500 divided by pi. Taking the cube root on both sides, and remember if it's odd, we do not put a plus or minus. So this works out to being the cube root of 500 divided by pi, which is approximately equal to 5.42 centimeters. And that's our units. We're in centimeters. And then we're talking this is our radius. So in order to see that this is minimized at this value, I need to make a number line. I'm going to start my number line at 0, and I'm going to put 5.42 on here. I need to substitute this into my derivative function, which we have. And I'll go ahead and box that. And I need to go ahead and see what is the derivative of something smaller. So we can substitute in 1, and something larger, we can do the surface area prime of 10. And so when you substitute in 1, you get something negative, so this is decreasing. And then when you substitute in 10, you get that it is increasing. And so we have a local minimum at 5.42. So we have a minimum at 5.42. And again, our units are centimeters. And then in order to find the other dimension, which is our height, I need to substitute this back in. The easiest equation to use, I will box. It's 1,000 divided by pi r. Our radius is going to be the cube root of 500 divided by pi. And then we have this squared. And this is approximately equal to 10.84 centimeters. So writing this down below, we'll say that this is going to be our surface area that will be minimized. The dimensions that will use the least amount of material will be our radius is going to be, and we'll say approximately equal to 5.42 centimeters. And our height of that can is going to be approximately 10.84 centimeters. The next example that we have, we are going to go ahead and circle that and look at that one together in class.